not here. It's not yet okay. Yeah, now the YouTube feed has started, so you can.
Okay.
She's fine. She's setting it.
Morning, everybody. Today is the fourth and the last lecture of the series, and today we will define the project, which many of you must have been wondering about where is the project all this time. So before start today, let me say a few words about the project. Is that because many of you, I understand, are young and probably would be doing a research project for the first time, uh, or maybe if not first time, then haven't done many such projects before. So for a research project, the person who is offering the project does not have all the answers. So in this case, I really do not know what the answer to the question we are going to pose is, and I also do not know what are the exact steps that we should be taking. So because it's a research project, we do not really know how things would behave and what results we would get. So we would probably uh, change our approach as and when we get new results. So what we will do today is sort of define a broad outline and the beginning steps. So we take these beginning steps, we see what we get, and from then onwards, we will decide what we will do next. So people who would take up this project, if some people do take up this project, they can then contact me directly about how to proceed and what needs to be done. If you get stuck, if you have a question, you want to discuss some concept, you are most welcome. I will give you my email address at the end of this talk, and so you are most welcome to directly discuss and proceed with the project. And depending on the number of people who takes up this project, we may have to divide up the task that would be there, but that will come to when some of you have shown interest in the project. And if people do not feel interested in the project, then my task is done today itself. Okay, so we start today. So today we would talk about the menagerie, the different astrophysical classes of neutron stars. Because you see, when we see an object in the sky, we do not immediately say that this is a neutron star. We see it as an astrophysical object. We're getting some signals from it. Then using our theoretical understanding of the stuff, we say, okay, so here is a neutron star which is behaving in this particular fashion because of such and such conditions, such and such parameters that the neutron star has. And here is another one which is behaving in a different way because of different parameters and so on. So so today we will talk about these observational classes, and then we will talk about the evolutionary pathways which may connect them. And if we have some time, we will talk about the new horizons in the field of neutron star research. And then we'll go to the Magnetar question, which is the project that we will define for this lecture series. So the observational classes. Now we have already talked about radio pulsars. That is the predominant class of neutron stars that we observe them as. So amongst about 3,000 neutron stars that we have observed so far. Almost 2800 are in this category. So the spin period ranges from about a millisecond to about some 30 seconds. The maximum spin period observed for a radio pulsar is 23.5 seconds. You should, if you want, you can remember that number. Surface magnetic field ranges from 10 to the power 8 Gauss to 10 to the power 15 Gauss, and uh, the energy of radiation comes from the rotational energy of the neutron star. And we assume a dipolar model for this radiation, and we estimate the magnetic field from the slowdown of a radio pulsar, which we have discussed earlier. Now, those objects, the radio pulsars, are called rotation powered because the energy is coming from at the cost of the slowing down of the neutron star. Now, there is another kind of neutron stars that we see in the sky. They are accretion powered. What happens is there is uh, a neutron star uh, which has a very massive star as a companion. Now, this massive star fills its Roche lobe, and material from it falls onto the neutron star. So there is this companion star. It's a huge big star, and there is this little dot here, which is the neutron star, and it's expanded a little bit here, and it has a strong magnetic field, and the strong magnetic field channelizes the charged plasma, that's the material which is falling from the big star onto the neutron star. And because this material is channelized on through the magnetic field, it gives away X-ray pulses. So these are also called X-ray pulsars, and the energy of this emission comes from the uh, material which is accreting onto the neutron star because it's falling onto a compact object, so it loses its gravitational energy, and that comes out as X-ray. So this is basically pulsar emission through the accretion of ionized plasma, which is channelized by strong magnetic field. This is completely different from the emission of electromagnetic wave from radio pulsars that we have seen earlier. Similar situation happens when the neutron star has a companion which is not a massive star but a small low mass star. So here is, for example, it could be a white dwarf, it could be a very low mass star, and so this picture is for a white dwarf, and here is the neutron star, and there is a big accretion disk through which the material is spiraling in. Now, look at this system, and please remember the previous picture where here is this big star, massive star, and there is the neutron star. But here there's this small star, and there's this accretion disk, and in the center is the neutron star. For comparison, this is the surface of the sun, and compared to that, that's the dimension of this accreting system. This is obviously a low mass companion. These are called low mass X-ray binaries or LMXBs. And what happens is in these systems, because of the evolutionary processes that a neutron star goes through in low mass X-ray binaries, because the time scales are very, very large, you know that low mass stars evolve over much longer time scale compared to high mass stars, which have shorter time scales. So the magnetic field has evolved and has become smaller. So the magnetic field is not very strong. So the material is not channelized through the magnetic field directly. So in most cases in low mass X-ray binaries, the material is not channelized through the magnetic field, and therefore we do not have X-ray pulsars. So we do not have X-ray pulsars in low mass binaries, low mass X-ray binaries, and what we have are bursts emission, because nuclear processes may happen after a certain amount of accretion, and we see X-ray burst. Though I must mention here that now we are seeing systems in low mass X-ray binaries where even though the magnetic field is not very strong, the accretion rate, the material that is falling in, is so small, it's so weak, the accretion rate is so weak that the magnetic field is able to channelize that material. And then in such systems, we see the neutron star behaving like an X-ray pulsars, and those are called accreting millisecond X-ray pulsars. We'll talk about them in a little while. And so such systems are there where the magnetic field is weak, but also the accretion rate is weak. And so once again, it behaves like pulsar, but in X-rays. So these are the two systems, two types of systems sitting in HMXBs, the high mass X-ray binary. The high mass refers to the mass of the companion, and similarly low mass X-ray binaries in which the neutron star is accreting material from the companion and it shows up as a X-ray source. So these are accretion powered neutron stars. Now, then we have another kind of objects, which are the magnetars, which we are interested in this lecture series. What are these? These are neutron stars with extremely large magnetic field, close to 10 to the 15 Gauss, and flares. So there is this very strong magnetic field, and it flares up, and we see bursts, soft gamma ray burst, or X-ray emissions from here. So these flares are somewhat similar, not exactly, but somewhat similar in nature from the outside, not from the inside. Somewhat similar in nature with the magnetic flares that we see from sun. As I have said, the interior of the sun and the interior of a neutron star is completely different, but outside the flare of the magnetic field, that is somewhat similar. So these are magnetars, and you see that the energy that is coming from this object is neither because of the accretion or because of the rotation. The energy source of this object is a strong magnetic field. So in most cases, it is suspected, it's not certain, it's suspected that the source of energy of these objects is the decay of this extremely strong magnetic field. So on the basis of all these observations, here is a summary of the various observational classes of neutron stars, of the neutron star menagerie. So there are, if I can classify them according to the process, the method of energy generation in these objects, then we basically have three classes. One is the rotation powered pulsars. I'm coming to the subclasses in a little later. The rotation powered pulsars, the accretion powered object, and internal energy objects, for want of a better name. Why do we see internal energy objects? These are not only magnetars, there are also other type of objects there where we do not exactly know what the source of the energy is, but some internal mechanism in something inside the neutron star is happening, which gives rise to their energy source. And because we do not really understand what's happening there, so we club them together and call that these are internal energy objects. Now, amongst the rotation powered pulsars, we have the classical radio pulsars. What are classical radio pulsars? They are sort of uh, run of the mill pulsars, have a period of the order of 1 second or larger, and magnetic fields in the range of 10 to the power 11 to 10 to the power 13 Gauss. Now there are these objects called recycled radio pulsars. What are recycled radio pulsars? These have much weaker magnetic field, 10 to the power 9 to 10 to the power 8 to 10 to the power 10 Gauss or so, and much fastest period. A different class of radio pulsars. Now you would say that, what about they have smaller spin period? They have a weaker magnetic field, but why should they be classified under a different class? Why that is, we will come to in a minute. Uh, and then there are rotating radio transients, which we have talked about in the context of nulling pulsars, that they appear once in a while, they have one pulse and then they disappear, and then they come again. So these are different classes of objects, but all of them have um, at their root the rotation energy, which is the source of their energy. And we have talked about the accretion powered objects in HMXBs and LMXBs. And these are different variations on the same thing. So that the different manifestations of such objects, we need not go into all these details. Then we have magnetars, which show up as anomalous X-ray pulsars or soft gamma ray repeaters. Then we have isolated neutron stars. What are isolated neutron stars? These classical radio pulsars are also isolated neutron stars, but why do we call these objects as separately as isolated neutron stars? Is because these objects are isolated neutron stars, and they may be radio pulsars, but we are not seeing them because maybe their beam is pointing in some other direction. We see them as single isolated neutron stars solely because they are nearby, and therefore their black body radiation, the heat left over from the time they were born in a supernova, so that heat uh, uh, is radiated away as a black body, and the radiation comes in the X-ray band, and we see them because that radiation is very faint, and we see them only because they are nearby. So we see them as isolated neutron stars. The energy is just the leftover energy from the supernova in which the neutron star was created. Then I have talked about compact central objects in one of the previous lectures, where the neutron star is born in a supernova, and it's not really seen as a classical radio pulsar. The suspicion is that the magnetic field has been buried because of fallback accretion, and after a while they would be observed as classical radio pulsars. But at the moment, they are not behaving like radio pulsars. So here is a picture of all the neutron stars in a magnetic field spin period diagram. Now um, this is a kind of celebrated diagram in the field of neutron star research, where you put all the neutron stars in this picture. Unfortunately, all the neutron stars that we have observed cannot be put in this picture because we do not know the value of the magnetic field. We do not have an estimate for the magnetic field for many of the objects. So therefore, all of them, all the neutron stars that we know of are not represented here, but um, a large fraction of them are there. So you see that here are the run-of-the-mill classical radio pulsars. And this is the region where we have the millisecond pulsars, which you say they are recycled pulsar. Why we say recycled pulsar, I'll come to in a minute. So these orange thingies are all radio pulsars, but this is the classical ones. These are the millisecond ones. These objects are not radio pulsars. These are X-ray pulsars sitting in high mass X-ray binary. So they have, as you can see, they have very long spin period and reasonably similar and high magnetic field. Now this blue, I'm sorry, the pink lines here with huge bars on them. These bars are not error bars. There is measurement uncertainty in the value of the magnetic field of these objects. These are pulsars in the millisecond range, but they are sitting in the low mass X-ray binaries. So they are accreting. That's why they have a different color. But the estimate of the magnetic field is very difficult in these systems, and there are huge uncertainties of these bars sort of signify the uncertainty in the magnetic field, but they are in the millisecond range period. So these are accreting millisecond X-ray pulsars. These red objects, which you can see a reasonably slow spin period between 1 and 10 seconds roughly, but extremely large magnetic field, these red objects, these are the magnetars that we are interested in. And even knowing anything, without knowing anything else, if you look at this picture, you can have an idea that there are different populations that are clearly visible in this picture. For example, this uh, bunch of what we call the classical or normal radio pulsars, this bunch here is definitely different from this bunch here. There's a clustering here, there's a clustering here, and these pink objects here, and they are, of course, they are accreting objects, and therefore they are very different. Also, these red objects, the magnetars, they also do not really uh, fall into this category. They seem to be having their own separate region in this magnetic field spin period diagram. So we clearly see these different regions of the spin period magnetic field diagram, and there are different types of observational classes sitting there. The idea here is to understand if some neutron stars are born in this region, some are born in this region, some in here, some in there. Is it the fact that we see different type of neutron stars in different regions of this diagram because they're born that way, or uh, could there be an evolutionary connection between them? So before we go into this understanding, let me tell you very briefly that if you look at this diagram without any bias, let us say that you do not know anything about neutron stars. If you look at this diagram, you would clearly see that this seems to be the region where most of the neutron stars are. So one can sort of put out a conjecture that the neutron stars, most of the neutron stars, when they are born, they are born with spin period and magnetic field such that they are in this region. Thereafter, something happens to them, and they move either to this region or to that region. It's also possible that some objects are born here and they move to this region here, or objects are born here and they move to that region there. Now, there is some problem with uh, having neutron stars born in this region and then moving up there. Why? Because then you have to jack up the magnetic field. Now, increasing the magnetic field of an existing neutron star is not an easy proposition, as we will see later. So one tends to believe that some neutron stars are born in this region and then they move down and merge into this region. We will discuss about all that, and this is actually the crux of our project that we are going to undertake here. So as I said, that there are these bunch of objects. These are the millisecond pulsars, and you clearly see that even if from this diagram, you clearly see that there is this bunch, and there doesn't seem to be too many of them, and there is one clustering here. So this cluster here may not be the same as an ordinary part of this cluster. And if we make this spin period histogram, then it becomes very clear immediately that you have a very strong Gaussian sort of peak here, which are the ordinary normal radio pulsars with a slightly longer spin period. And you have another very clear Gaussian like peak. And these are the millisecond pulsars. So therefore, these two are clearly two different populations, and we can talk about them separately. So there has to be some, these two are different. Uh, to begin with, is there a connection or not? That has been one major area of research, and even I did my PhD in that area. So now people believe that there is a connection between these two. Gets these pulsars because some of the neutron stars are processed in binaries. You have talked about neutron stars sitting in high mass or low mass X-ray binaries. So if they have a companion, material falls onto the neutron star and processes happen on them, and then they can appear as millisecond pulsars after the accretion process ends. So here is how we separate them. So normal pulsars, which are mostly isolated, they do not have a companion. Magnetic field ranges from 10 to the power 11 to almost 15 Gauss, almost to the Magnetar range. I'm sorry. And millisecond pulsars, which mostly are sitting in a binary, these circular objects are binary objects. So you can clearly see that in the millisecond pulsar range, most of them are in binaries, obvious, because they are uh, processed to millisecond spin period because of being in a binary, because they do have either have or had a binary companion at some point of time, and the spin periods are roughly less than order of 30 milliseconds. Now, even among millisecond pulsars, we have noticed that depending on where in the galaxy are they located, they have different parameters. And this is what you see there. Just a second. Yeah. Uh, I'm sorry. Yeah. So this is in the globular clusters, and this refers to the galactic disk. Now you know globular clusters are sort of spherical stellar clusters at the outer edges of our galaxy, and they're very dense stellar they're very high stellar density in those clusters. And what you see there is, because we are looking at the millisecond pulsars, so the spin periods are roughly similar. The average spin period is roughly similar, even though in the galactic disk the spin period is slightly larger, but that can be it's not very larger. But if you look at the magnetic field, you see that in the globular cluster, the magnetic field is significantly higher compared to the magnetic field in the galactic disk. And we have looked into this problem, and we believe that this difference in the intrinsic parameters of the neutron stars appear because in the globular clusters there is high probability of stellar collisions. So a neutron star which has a particular companion today may not have the same companion after an amount of time, because of the high probability of stellar collision. That companion may be replaced by another companion, or uh, it may simply lose its companion. So the nature changes, and also the nature of the evolution changes, and that uh, results in the globular cluster millisecond pulsars having slightly larger magnetic field, sometimes almost twice or three times the magnetic field the average value of the magnetic field in galactic disk. So this even the external environment can play a major role in the evolution of the internal parameters of an object. So now let us talk about the evolutionary pathways. We have already started talking about the evolutionary pathways. So it's we just continuing. So as I have said that we are talking about recycling of the objects, and we believe that, I'm sorry, we believe that neutron stars in here, neutron stars with parameters corresponding to the population here, if they have a binary companion, then they would go to this kind of population. Now, there are two types of companions that they can have, as we have already noted. It can have a low mass companion, or it can have a high mass companion. So the calculations show that if a neutron star is having a companion which is a low mass companion, then the recycling process goes on for a much longer time, and those neutron stars would end up as millisecond pulsars with much faster spin period and very, very weak magnetic field. On the other hand, if a neutron star has a more massive companion where the time scales are much, much shorter, they would be recycled, but they would probably be mildly recycled. So the spin period would not be too small, and the magnetic field also would not go down very much. So, and now you see that we actually have a smaller peak in between. So there seem to be another population sitting there, which probably corresponds to the recycled objects coming from high mass X-ray binaries. So now this is how we can understand the evolutionary pathways of a normal neutron star in general. So we have young neutron stars, young pulsars spinning rapidly and possessing a strong magnetic field. Now they are slowing down. We know they are slowing down. So they slow down. Old pulsars have slower periods, and this picture says weaker magnetic fields, but there is an uncertainty about this particular issue, whether isolated pulsars have significant decay of the magnetic field. And many people have shown through their calculation that the decay of the magnetic field in isolated neutron stars is not significant. Including our group, we have shown that that may not be significant. So what the pulsars would do is, because they're slowing down, the spin period is getting longer, so the pulsar would move sort of parallel to the x-axis and move like this. Now here is a line which is called a death line. What is a death line? It is a combination of magnetic field and spin period below which the process of emission does not work. As I have explained in the first lecture itself, the magnetic field, the magnetic field in the neutron star, because it is rotating, it creates a strong electric field which either creates or pulls out charged particles from the surface of the neutron star, or there are charged particle electron positron pair production in the electric field there, and these are the charged particles which should move along the magnetic field lines and would give rise to the pulsar emission. Now that process cannot be effective if we are below a certain combination of magnetic field spin period. As you can guess, strength of the electric field generated would be much weaker, and therefore the process would not work. So a pulsar, when it slows down too much, or if it has magnetic field decay, it crosses this line, then it does not remain active as a pulsar. The emission process does not work. So this is called a death line, below which a neutron star is no longer acting as a pulsar. Now, when it comes to this part, it's still there, it's still a neutron star, it still has rotation, it still has magnetic field. At that point of time, if it does have a companion, then this companion is transferring material onto the neutron star, which would, because it is coming via an accretion disk, uh, so it would bring in extra angular momentum. And if extra angular momentum is added to the neutron star, then what happens? Then the neutron star is spun up. So it starts moving in this direction. So its spin period starts getting shorter. Also, because of material accretion, the crustal region heats up, and we have discussed in last week that when the crustal region heats up, it will weaken the magnetic field. So what it does is the magnetic field goes down. So let us say a particular pulsar is here, crosses the death line here. Because of the process of accretion, it has crossed the death line here. Because of the process of accretion, the magnetic field comes down and spin period also comes down. So it will cross the death line in this direction at some point if it has a companion from which mass is being transferred. So what happens is then it reappears above the death line, and that's what we call is recycling of a pulsar. So therefore, this millisecond pulsars, the pulsars with very, very small spin period and weaker magnetic field, are processed through an accretion channel, and they are recycled and they are reborn. They come up uh, from beneath the death line, they emerge again. So this is something like the picture that I am talking about. Here is a normal pulsar, and there is a recycling, and it comes up and appears here. There is a spin-up line also, which corresponds to the maximum amount of spinning up that a neutron star can go through. So a neutron star cannot be spun up indefinitely through the process of accretion, because we know that there is a limit to the rate of accretion that can um, uh, happen on any astrophysical body, and that is called the Eddington rate of accretion. I'm sure people who are familiar with certain astrophysical processes are familiar with Eddington rate of accretion. Now, at the rate of Eddington rate of accretion, the spinning up would be maximum, and there would be a value of the spin period corresponding to a particular value of the magnetic field. So at every magnetic field, there would be a maximum, minimum spin period to which a neutron star can be spun up, and therefore you have a spin up line. And all the millisecond pulsars that you see today are very close to the spin up line. So they have been maximally spun up through the process of accretion. So here is a summary of radio pulsar recycling. Here are the systems. So solitary pulsars do not go through any recycling. They have 10 to the power 11 to 10 to the power 13 Gauss of magnetic field, and it remains there. In high mass binary pulsars, neutron stars have massive companions. And the magnetic field, the final magnetic field that we see are usually larger than 10 power 10, 10 power 11 Gauss. In low mass binary pulsars, there are low mass companions, and the magnetic field goes down to about 10 power 8 to 10 power 10 Gauss. So in low mass X-ray binaries, we see the maximum decay of magnetic field and maximum spinning up of a neutron star. We would skip that. So in high mass X-ray binaries, through ohmic dissipation, what we find is this is the spin up line and this is the death line. Most of the objects are recycled back into this region. And for low mass X-ray binaries, we would see that most of the objects are recycled back to this region. Now, in low mass X-ray binaries, the pulsars can be recycled. I'm sorry, pulsars can be recycled. Um, Now, these are the objects which would be recycled in this region. And you see that these are some theoretical curves along which there can be magnetic field, I'm sorry, neutron star recycling. And you see that only around these parameter values, these are parameters for some calculation. Let us not worry about what those parameters are. But you see that we can tweak the parameter values such that we have neutron stars appearing in the region where most of the millisecond pulsars are. That tells you that those are the parameters which are relevant for the neutron star physics in the low mass X-ray binary systems. So here is one way of validating our theoretical calculations. So we set up our theory and we do calculations, and of course we do not know exactly what kind of parameter values. What are the parameter values? Now I can tell you what the parameter values are. The parameter values correspond to the amount of impurity in the crust of the neutron star, the density at which most of the currents are concentrated, the temperature of the neutron star crustal region. Now, all these parameters, of course, I have no idea of knowing what those parameters are, but I do my calculation and I match my final products with the products I see on the sky, that is the millisecond pulsars, and then I immediately know what those parameters values should be. So that tells me that what is the impurity concentration on the crust of a neutron star, what is the temperature in the deeper regions of an accreting neutron star, what is the density at which the magnetic field supporting currents are concentrated. So all that understanding about the interior of the neutron star comes from this kind of calculation. I remember last time a person asked a question, how do we know what is there inside a neutron star? This is how we figure out what is there in the inside of a neutron star. This is one example. Okay. Now there are accreting millisecond X-ray pulsars that I have talked about. They are millisecond period X-ray pulsars sitting in low mass X-ray binaries. As I have said, in low mass X-ray binaries, when the accretion rate is too small, when is it too small? When the accretion is about to end. So at that point of time, because the accretion rate has become very, very weak, the magnetic field, even though we can channelize this material, and we have accreting millisecond X-ray pulsars. Now, a vindication of this understanding of ours that here is a millisecond pulsar which has been recycled in this low mass X-ray binary, but now the accretion phase is kind of ending, the rate of accretion is tapering off, and this is kind of that phase is ending, so it's slowly appearing as a pulsar again. There is a vindication of such a scenario when this object, the first transitional pulsar, was observed. What is this transitional pulsar? It was first seen as an accreting millisecond X-ray pulsar. It's accreting, and it's because the accretion is very, very weak, and it's showing up as a X-ray pulsar. But because the accretion is tapering off, there are phases in which the accretion actually stops. So the accretion has become so weak, there are phases in which the accretion completely disappears. Now, the moment that happens, this object shows up as a radio pulsar, like a normal radio pulsar, a millisecond radio pulsar. And then after a while, when the accretion resumes, it again goes back to its accreting millisecond X-ray pulsar phase. So therefore, here is an object which we are seeing both in accretion, when the accretion is active, And as a radio pulsar, when the accretion has stopped, so we clearly see the connection between accretion and the recycling of a neutron star. So this is a very clear vindication of our theoretical understanding of how an ordinary neutron star, by ordinary I mean slow spin period, about 1 second or thereabouts, or larger, and stronger magnetic field 10 to the power 12, 10 to the power 13 gauss, how such a neutron star can be processed in accreting systems to give rise to millisecond pulsars, which have spin period closer to millisecond and much weaker magnetic field. So now, so we have understood sort of how the process of recycling happens. So let us look at the overall interpretation of pulsar recycling. So this is the familiar picture. We have come back to it again with a death line and a spin up line added to it. So this is our island of uh, spin period magnetic field mm, region, where we believe most of the neutron stars are born with that kind of parameters. And during their lifetime, because they are radiating at the expense of their rotational energy, they slow down and move to this region. And this is the region where we see them as accreting pulsars, because please remember, in this region, even though it is beyond the death line, the process of emission is totally different. Material is falling onto it, it's accreting, and therefore it's radiating in X-ray. So there is no constraint on the combination of the spin period and the magnetic field. So it doesn't care about the death line, and it can show up as X-ray pulsars no matter how slow it is. And precisely because of that, we are seeing them far beyond the radio pulsar death line as X-ray pulsars here. Now these objects, after being processed in X-ray binaries, they will show up as millisecond pulsars here. Also, if the companion happens to be a massive companion, that is, the system is HIMARS X-ray binaries, then they would show up not really there, but somewhere in between. So these are the objects which are being processed in HIMARS X-ray binaries. In summary, we have radio pulsars. Now, there are different kind of subclasses. One is the millisecond pulsar, and there are long period pulsars. Now, amongst the long period pulsars, there are high magnetic field and intermediate magnetic field. And on the other hand, we have X-ray binaries, which have two types: high mass X-ray binaries and low mass X-ray binaries. So a neutron star sitting in a low mass X-ray binary gets processed and shows up as accreting millisecond X-ray pulsar, and then goes on to become a millisecond radio pulsar. On the other hand, if it is sitting in an HMXB, high mass X-ray binaries, then it shows up as a reasonably long period but intermediate value of magnetic field. So reprocessing in accreting system gives us a reduction in the magnetic field, a reduction in the spin period, and also a reduction in the spin period derivative, which is obvious because the magnetic field has gone down. So it is not only very fast, it's slowing down at a much lower rate. So it's a very fast spinning top, which has a very slow spin down rate. So now here are the evolutionary links. The rotation powered pulsars and the accretion powered objects are connected. We have already seen. This connection is through binary association. Now, here are these internal energy objects, and we believe that they are connected to these rotation powered pulsars through a magnetothermal evolution. One has to remember that there is no external agency for these internal energy objects. They are not in binaries. They do not have a companion, so therefore there is no material accretion or any such external agency working on the neutron star, which would modify the properties of the neutron star. But of course, because a neutron star is not a static object as far as evolution goes, so there exists process of magnetothermal evolution in a neutron star, and that probably is the process. A lot of work has been done on this magnetothermal evolution, which connects a classical radio pulsar to these other forms of neutron stars, which some of which we have already discussed. For example, we have already said that the central compact objects would probably show up as classical radio pulsars once their buried magnetic field re-emerges, or these isolated neutron stars are probably actually acting as normal radio pulsars, but their beams are pointed somewhere else, so therefore we do not see them as classical radio pulsars. Our aim here is to understand how magnetars can be connected to the classical radio pulsars. So we would skip the new horizons part, in which I wish to talk about various new telescopes and instruments which are coming up, which helps us understanding the neutron stars even better. But because it's already close to 11 and we definitely need to talk about it, so I'll go on to that and skip this section altogether. Okay, so here were we. When we understand these connections very well, now here is this island of these red dots, which are the magnetars, and I have said we do not understand whether these orange objects go there or those red objects come here. We do not understand that, and that is what we would like to understand through the project we aim to do.
Sushan, we can't hear you. Sushan. Hello, Sushan. Okay. Actually, we'll have to go back inside. I stopped the recording, huh? Hmm? I stopped the recording. Is she coming back? Sorry. Yeah, we can continue. Sushan, you may have to repeat a little bit because I think when you went off.
Yeah, you have to allow me to share my screen again.
Oh, sorry.
Uh,
Sorry.
because all the settings are gone now.
Yeah, okay, no problem. You're back.
All right. So we are talking about the Magnetar question now. So here are the pathways that we have already seen, and we kind of understand this part of the diagram. So the lower part of the diagram we more or less understand the interconnections between all these, but we certainly do not understand this part anymore, right? As I have said before, whether these orange dots under suitable conditions would go over here, or I'm sorry, or the red dots under suitable conditions would move here, is the question that we would like to address in the project that we aim to define. So, and as I have said, this is the connection we want to explore: the classical radio pulsars to the internal energy objects. In other words, when I say classical radio pulsar, I basically mean objects in this orange island, neutron stars with this range of spin period and this particular range of magnetic field. And we want to connect that kind of objects to the magnetars, which are basically here. So these objects are relatively slower compared to these ordinary, the regular objects, and they have much stronger magnetic field. As you can see that the strongest magnetic field is about 15.5, 10 to the power 15.5 Gauss. So this is really very strong magnetic field, and they are overall they are much slower compared to these orange objects. So what we would like to now understand is, this is one set of objects that we have understood, that compared to these ordinary set of objects, they have weaker magnetic field and they have faster rotation, the shorter spin period. Now we want to understand another set of objects which have stronger magnetic field and slower rotation. Now, as I have said before, if you want to increase the magnetic field of a solid object, that is much more difficult than decreasing, because decreasing a magnetic field is very easy. You have to somehow turn on the ohmic dissipation process. So there is a magnetic field and you want to dissipate it somehow. So there are processes through which you can dissipate the magnetic field. But jacking up the magnetic field, you want to increase the magnetic field of an object, that is not so easy, particularly because we really have not understood very clearly the process of magnetic field generation itself. So we do not understand how such strong magnetic fields have been generated, and now we want to increase the magnetic field, which is a higher order difficulty, if you ask me. And so therefore this is not a situation which we can easily handle. So we have to go
Hello everyone, just hold on. Yeah, I think she had some power problem, probably thanks to the rains. So just hold on. She'll log in. Hmm? मैं अभी बात कर रही हूँ.
Priya, I got disconnected again, so you have to again allow me to share the screen.
Yeah, Sushan, lots of
Yeah,
rain in
yeah,
because
okay.
here it's pouring. Here it's pouring.
Yeah,
There's
I got
one.
disconnected again.
Yeah, yeah, okay.
Yeah, now it's working. Now it's
One.
working. Yeah.
Okay.
So I'm visible.
Are you co-host still?
Uh,
All fine.
uh, is my screen visible?
Yeah,
Oh, okay,
yeah.
okay. I'm sorry. There's this disturbance today.
No problem. So this is evolutionary links. That's like
Yeah.
it.
Okay. Yeah. Okay. So so therefore, this is what we are trying to understand. Now, if you remember, when in the context of glitch, we had already talked about something that gives us a hint of how evolution can happen in a neutron star, which does not have an external agency, in other words, accretion effective on it. So when an ordinary neutron star undergoes spin down gives rise to expulsion of rotational vortices, and because of the interpinning with the magnetic fluxoids, that would cause expulsion of magnetic fluxoids. A glitch gives rise to increased magnetic stress at the core crust boundary, so that may lead to crust cracking. That also may lead to expulsion of magnetic fluxoids. Now, this flux expulsion, so there is some deposition of the flux at the core crust boundary. Now, this flux goes to the metallic crust and there can be ohmic dissipation. Now, all this is telling you that you may expel some crust from the interior and it comes to the crust and that it gets ohmically dissipated. Now, all this is telling you that the magnetic flux would be decreased, not increased. Now, there is only one possible way in which we can think of increasing of the magnetic field is also through this process. How? There could exist screening currents at the core crust boundary. Now, if there are screening currents, then the magnetic field residing inside the core region would not be observable from outside. So suppose there is a very strong magnetic field, you have generated a very strong magnetic field. Suppose you have a magnetic, a strong magnet, that the kind of magnets you use for the fridge stickers, they have some magnetic field. So you can do this experiment at home, and you know that if you put that sticker inside a metallic box, and then the magnetic field gets screened. So why? Because screening currents, diamagnetic currents are set up in that metallic box. Now, similar diamagnetic screening currents may be present at the core crust boundary, hiding a much stronger magnetic field in the core of the neutron star. Now, if such is the case, then flux expulsion at the core crust boundary and diffusion of that magnetic field towards the surface would actually give rise to increase in the observable field. You are not, I'm sorry, you are not actually increasing the field inside the neutron star. It's basically one part of the magnetic field you are not seeing before has now been visible. So there is a stronger magnetic field hidden deep inside the neutron star, and because of the process of glitch or some other process through which this flux has been expelled from the core region, can become observable, and that would give rise to an increase in the observable magnetic field. Now, as I have mentioned, in the context of glitch, there are some glitching pulsars in which people believe that they have observed an increase in the magnetic field, and such an increase can be understood this way. So therefore, if this is the process that is happening in glitching pulsars, then an ordinary radio pulsar can go to magnetar fields, that is, it has a magnetic field and which goes on to increasing because of certain processes that are happening, and in any case it is slowing down. So therefore a radio pulsar slows down, it becomes slower, and it increases its magnetic field, and therefore it can actually move from this region to that region. One has to reckon that this is a possibility, of course, but uh, one really does not understand the process through which such flux expulsion from the core region of the neutron star to the crust would happen, which would kill the screening currents. You have to remember that the presence of screening currents is what is very crucial for this scenario to work. So we are assuming that there exists a screening current which somehow has been killed, and therefore we are being able to see the magnetic field which was hidden inside the core. Now this process has to be properly worked out and understood, and there is a lot of uncertainty in this physics. So there is a suggestion, but it hasn't been really sort of accepted by the community yet. So this is kind of a summary of the evolution of isolated pulsars. I have to remind you once again that a similar picture that we had seen in the context of binary neutron star and in process of accretion, that picture is really agreed upon by people in the community, whereas this particular picture, this is a conjecture, most of it is conjecture, and we seriously do not know whether all the arrows here are correct or not. Okay, so this is still in a state of conjecture. So what do we know? We know that ordinary radio pulsars, they slow down and they become dead pulsars. That much we know. They also have some of the ordinary radio pulsars undergo glitch. Do they move up to magnetar fields? We do not know. Ordinary radio pulsars through field burial become central compact objects. Do they would they come up as ordinary radio pulsars after a certain amount of time? We do not know. Ordinary radio pulsars show nulling. Some of them are intermittent radio pulsars. Are they connected to RRATs? We do not know. Are RRATs connected to magnetars? We do not know. Do central compact objects emerge in the region of magnetars instead of ordinary radio pulsars? We do not know. All these arrows are in the range of conjecture. People have suggested that these are possible evolutionary pathways, and it's possible that this is how the neutron stars behave. But so far, we really are not certain about many of these pathways that are indicated in this picture. So what we are trying to do, we are trying to connect these ordinary radio pulsars to the magnetos. Now, the summary of evolutionary links. Pulsar recycling connects isolated milliseconds
She's gone.
Uh,
One second. She's gone.
yeah, I'm so sorry for the repeated
नहीं नहीं
interruptions.
but do we blame the rain gods or
My apologies for the repeated interruptions. Okay, so we are talking about the pulsar evolutionary links. So pulsar recycling connects isolated millisecond pulsars to AMXPs to cluster millisecond pulsars and so on. There are all these connections, and one needs to understand null pulsar are that connection, glitch induced evolution, CCO, magnetar link, and this is that we would look at. Now, one bit of interesting physics that I would like to tell you about is that we have been talking about transition between these objects and these objects, and we are saying that maybe there is glitch induced evolution from the ordinary neutron stars, ordinary radio pulsars to the magnetic field. We do not know whether that process would work. As I have already told you that it depends on various very complex assumptions, the physics of which we do not really understand very well. But there is so here is this region in which we have the magnetic, the strong magnetic field objects, that is the magnetars. Strongly magnetic would give rise to strong gravitational waves. Now, this was worked out by wave would be such that these would not be observable by any of the existing gravitational wave observatories that are working today. So this is the region in which we have all our magnetars. Now, had these magnetars been sitting in HMXBs, the kind of gravitational waves they would be generating would not be observable by the gravitational waves, because look at this shaded region, that is the extreme limit of the gravitational wave observatories that you have today. So therefore, only if this box were shifted to this, A were shifted to B, then only we would be able to observe them in the gravitational wave, using the gravitational wave observatories. But of course, we do not have neutron stars in this box B. We only have neutron stars in the box A. And those would be observable in some of the gravitational observatories that have been proposed to be built in future. So those observatories would probably come up in 10-20 years time. And if we see uh, young neutron stars, young uh, magnetars via these gravitational wave observatories, then we would know that where these magnetars would be in time of their in the phase of evolution, whether they are born as magnetars, or these objects somehow transition into magnetars. Now, there is one that millisecond magnetars are born. That is, magnetars are born with millisecond periods. That is, they are actually born here. Very strong magnetic field, but millisecond spin period, they are actually born here. But because they have a very, very strong magnetic field, within a very short time scale, astronomically short time scale, and therefore the process of radio pulsars moving to magnetars would not be a path that would be generally followed. So basically what we are saying is we have millisecond magnetars which evolve very fast. They just slow down very fast, retaining their magnetic field. So they move from B to A, and then something happens to them or does not happen to them. So now, therefore, our task would be, if we want to see if there is any evolutionary connection between I'm sorry, connection between these neutron stars and the magnetars, then the pathway that we should explore is from the magnetars to the radio pulsars. So then what we are looking at is uh, these objects which have stronger magnetic field, slower rotation, should move over to weaker magnetic field and faster rotation. Now we have a reverse problem. If we were going from here to there, then slowing down was not a problem, because pulsars do slow down, but jacking up the magnetic field was a problem. Now we have a problem of getting the neutron star to rotate faster, because uh, dissipating the magnetic field through which
We can't hear you, Sushan. Your mic is off.
I am sorry, because of all these interruptions. I think I did not unmute myself this last time. So I'll repeat what I was saying. So what we want is, we understand that the magnetos probably are born here in this box B. Uh, we should be able to see some this region A, where we are seeing them today as magnetars. And what we want to do is find a connection between these objects and this population. So we would like to process which reduces the magnetic field. That is easy. Magnetic field can be dissipated, but that also spins up the neutron star. And we have seen such a process to happen through accretion when a neutron star has a binary companion and material is transferred from the companion to the neutron star. But such a process would not work here, simply because the magnetons that we are talking about do not have a companion. So therefore, the process of accretion, which was very effective in the transition from this island to that island, cannot be invoked here. So we have to try to figure out what is it that can possibly connect these two populations. And before we embark upon this project, let um, give a forewarning work on this, is that there is no possibility that we would find a process through which these two populations would be connected. Nevertheless, we should be able to show that these populations are different, and whether or not there exists an evolutionary connection is something that we would like to establish. And so what we do, we would first want to look at the radio pulsar population, and extract the parameters of a pulsar. I will show you in a minute. Then we go to this other website and look at the magnetar population, uh, find the parameters from there. Then we try to figure out the interconnected behavior that are seen in many of these objects. And then we look at the evolutionary pathways. So what now I will do is take you to this website and show you what we would do to begin with. We would look at the spin period distribution and surface magnetic field distribution of populations, the radio pulsar population and the magnetar population. And we would then try to look at the correlation, the spin period correlation and the magnetic field correlation through Kolmogorov-Smirnov test. And people who are not familiar with Kolmogorov-Smirnov test, I would suggest that you look it up in a statistics book. And there are sites on the web which you can use to find correlation. If you give data for two different populations, there are sites through which you can the results of the case test. But in order to understand what numbers you are getting from the case test and what the case test is doing, you really have to know what a case test is. So people who are not familiar with that, I would suggest that please go and look up case test from some statistics book. And in order to perform the case test, we also have to do random sampling of radio pulsar population. Why do we have to do a random sampling? This is a part of the code that you have to write. Uh, if you wish to write that, I will help you in whichever language you want to write. Why do we need a random sampling? Please remember that if we go back to this picture once again, yeah. So you see that these orange dots, you may not be able to sort of count them, but you can see that there is a large number of these orange dots. There are actually about 17 to 1800 out here in this orange region. Whereas these objects are 30 in number. I do not have all 30 plotted here. Many of the magnetars do not have the magnetic field estimated accurately. And if I do not have the magnetic field, of course, I cannot put them in this plot. So, but there are about 30 magnetars that we know about. And so therefore, you cannot compare two populations, which has some 1800 points and the other one has 30 points. So these two populations cannot be compared. And then compare with the magnetar population. Then, but one such random sample would not give you a robust result. So what you have to do is times as possible, maybe 1,000 times, million times, till your result saturates. You have the same kind of correlation that you which does not change even if you increase the number of tests. So what one has to do is take this huge population of radio pulsars and randomly choose 30 out of them, compare with the magnetar population and write down the result of the case test, and then repeat this process again and again and again till the average value of the case test sort of saturates. So for that, you have to call upon a random number generator, which will use, if you number the pulsars that are here, if you number them, the random number generator would take the numbers, or you have to devise how you randomly sample 40 out of these 1800, almost 2000. I'm sorry, it's 2500 now objects. So that is a part of the code that we can later on. So that's what we will do. We will first look at the spin period distribution, magnetic field distribution, and period and magnetic field correlation using the case test. Now, what do we obtain from here? We basically, from there, we will, if we say that the magnetic field need not evolve for a magnetar or a radio pulsar that is there. So we artificially stop the magnetic field to evolve from evolving and see how the neutron star would change its period, both for the radio pulsar and the magnetic field. And we see where the population goes. When the spin period changes, it goes and occupies a different area of the spin period magnetic field diagram. So we see where the population goes, and from there we would do some back calculation. We would put in some arbitrary field evolution form in the evolution of the neutron star, both for the radio pulsar and for the magnetar. Now, field evolution either of radio pulsar or magnetar is a complex process. Now, before we go into that kind of complex coding, what we can do is we can very simply put a magnetic field evolution as in let's say we can assume it to evolve exponentially or through some power law, and use that to see whether we can from radio pulsar we can go to magnetos, or from magnetos to radio pulsars. And only after that, once we have seen that, we would try to see what could be the processes through which a magnetar could be how a magnetar could become a fast rotator, a faster rotator. So please remember that the ordinary radio pulsars have weaker magnetic field, but they rotate on the average faster than the magnetars. So we would have to see what are the processes and people who choose to take this up, if anybody chooses to take this up, you can contact me directly through this email address. And if you have questions, queries, anything, I would be happy to answer that. Now, before we finish today's session, let us go to these websites, these two websites that I have talked about. And I'll close the presentation and take you to these websites. Now, here is this catalog. I'm sorry. So this is called the 80th pulsar catalog. And here you will see all the pulsars, all the radio pulsars are listed here. And you can call any parameters that you wish to look at. You can call up any of the parameters, and various parameters have been explained in the documentation, in the tutorial. For example, the pulsars are most pulsars have two names. One is the B name, one is the J name, which basically depends on two different kind of naming system which came before 1950 and after 1950. So it doesn't matter. So these are names. Okay. So let me say that I want to know the name of a pulsar, which may or may not be useful. I want to know the spin period. And I also want to know the first derivative of the spin period. And let us say I also want to know the magnetic field of a pulsar. And then there are, it can sort on various quantities. If you want to sort it on, let us say I want to sort on the spin period, the ascending value of the spin period. And then I want to have the table. So okay, so this is what it gives me. As you can see, there are a string of objects which does not have a spin period listed. So the spin period has not been calculated precisely for them. So of course, those objects we cannot do anything about. We cannot use them in our calculation. And then there is number of objects, and you will see that for many objects you have a spin period. There isn't a value of the period derivative, and therefore there isn't a value of the magnetic field. So precise measurements have not been done, and therefore no value is being quoted. So again, you can only use the spin period. So there will be many objects for which you so when you look at the spin, you have a certain number of objects. When you look at magnetic field, you have a smaller set of objects. So this is what you can do with this site. It also has a feature which is called type. I cannot see, yes, type, which will tell you what kind of object it is. Let me show you. Very long. Okay, it's taking. Magnetar names are slightly different, but many of these objects are also in the ATNF catalog, but they are slightly different, but they might be similar, same object. So here, spin period, period derivative, magnetic field, etc. are given. But once again, there will be objects for which all the quantities are not there, or none of the quantities are available, and so on. You only know that these exist. So you can take the values from here, and when you get all these values, what you have to do is first create spin diagrams for the pulsars and spin period diagram for the magnetars, and do the same for the surface magnetic field. Once that is done, then we'll go to the correlation, that is the case test. Okay. So here it says pulsar type. You see it, many of these are called RLATs. Many of these are HE, that is energy. These are radio pulsars, but they are not seen in radio, but they are only seen in high energy, etc., etc. But nevertheless, they are basically going through the same process as radio pulsars. It's only that they are not seen in radio. Okay, no, I'm sorry. These high energies they are seen in radio as well as in high energy. These NRAD also, these are radio pulsar not seen in radio. They are only seen in high energy. Okay. So here is an object which is called XP, is anomalous X-ray pulsar. These are the magnetars. So magnetars are seen as anomalous X-ray pulsars or soft gamma ray repeaters. Okay. So all the magnetars that are listed in ATNF catalog, they are listed as AXPs. So they are not listed as magnetars, but these are the magnetars that are listed in ATNF. So ATNF catalog is an overarching catalog. So it has all kinds of stars, barring the acting systems. HMXBs and the LMXBs are not listed here, but everything else is listed here. So all the magnetars that you see in this catalog are also in the ATNF catalog. So when you do a spin period histogram for from for the radio pulsars from the ATNM catalog. Remember to take out the ASPs, and there are also several objects which are extragalactic. We do not want to contaminate our data, so therefore objects also. So if you in the association, then it would tell you whether it's whether it is object or not. So in the association column, would say X-galactic. We would remove all the extragalactic objects. So when you start doing people who wish to do the project, please write to me, and then we can have a separate session as to how we proceed with this work. Or if you have individual questions, I would be very happy to answer individual questions about the project. Yeah, we have this association. See, here are various associations. That these are not important. So it is. It means that it is an
Please unmute.
extragalactic object. So we would remove all
Unmute
these
your.
extragalactic objects. Given that I am sort of I have said whatever I wanted to say, and there is this huge amount of disturbance today because of the power fluctuation, I would finish it here. Thank you everybody for listening, for tuning in every time. And if you wish to do the project, please contact me and we will take it forward. Thank you very much. Priya, am I audible?
Hello.
Hello, am I audible?
Yeah, we can hear you. We can hear you. It's coming here. And there were some questions which you probably lost because of the fluctuation.
Yes, I cannot see any question in the group chat.
Yeah, so I'll just repost it. Okay, I'll just repost it. Yeah, so here is the first one.
Okay.
What is the time scale of recycling and so on? Yeah, you can
Can
read it.
two magnetar merge like normal neutron stars? Yeah, if I mean, these are basically neutron stars with very strong magnetic field. So, as you know, in 2017, we had had an event which was detected by the gravitational wave LIGO-Virgo collaboration, and then it was followed up in electromagnetic signals world over, including our GMRT, where two neutron stars merged. Now, if two neutron stars of magnetar magnetic field strength merge, they would merge. If they are in a binary which is spiraling in, yeah, they would merge. No problem with that. Okay, second question. Why does the rate of spin of the neutron star goes up while it is accreting matter? As the moment of inertia increases, okay, the increase in the moment of inertia is actually negligible, and please remember that because of the nature of the equational state of neutron star, when the mass increases, the radius actually decreases a little bit. Okay, so the change in the moment of inertia is absolutely tiny compared to the total angular momentum that is coming in. So what happens is the spin actually increases. What is the time scale of recycling? Time scale of recycling is actually the time scale of the evolution of the Loma star. So the time scale and the accretion phase that is available in the X-ray binary. So for low mass X-ray binaries, the time scale is of the order of 10 to the power 9 years, whereas in the high mass X-ray binaries, because the massive stars evolve much faster, the typical time scale, the accretion phase is very, very short. So it could be even as short as 10 to the power 4 years, from 10 to the power 4 to 10 to the power 6 years is the time scale of recycling, depending on what the companion star is. Does a globular cluster have only a certain type of pulsar? No, 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 not a certain type of pulsar. There are different kinds of, there are neutron stars, and the difference between a globular cluster neutron star and a galactic disk neutron star is, in globular cluster, it may not have the same companion throughout its evolutionary phase, whereas in the galactic disk, if it starts its life with a binary companion, it's most likely that it would have the same companion, unless the binary is disrupted, have the same companion throughout its evolutionary phase. Is the spin period magnetic? Is there an age dimension plotted? No, there is no age dimension plotted. As I have said, age estimate of a pulsar comes from P and P dot. And when you look at the spin period magnetic field diagram, for the radio pulsar, the magnetic field is the dipolar magnetic. For radio pulsars, the spin period and P dot, the spin period and age, and the spin period and the magnetic field is the basically same diagram drawn in different ways. But other kind of objects for which the magnetic field comes from some other consideration, not from the P dot, then the magnetic field and spin period diagram becomes not equivalent to the spin period and age, spin period and P dot diagram. So therefore, this diagram is does have age, but only for radio pulsars for which age comes from P and P dot, as does the magnetic field. I have already answered why the why the rate of spin period goes up during accretion.
Sorry,
Time
just
scale
cut
recycling,
pasted.
that is
Then
also has been given.
there are some repeated.
The LIGO limit, does this limit depend both on magnetic field and rotation period, or only on rotation period? Yeah, this limit both depend both on magnetic field and rotation period. Why rotation period? Because the frequency of the gravitational wave emitted from a stably rotating neutron star. We are not talking about a merger here. We are talking about a rotating neutron star and gravitational wave coming from it. Because there are some surface undulation on the neutron star, the frequency of the gravitational wave is related to the spin frequency of the neutron star. So that way it is connected.
Yeah. I think there are no questions more. Though I think a lot of problem happened because of the breaking today, right?
Yeah.
When actually today was the main focus one with the with the project.
Yeah.
And that was sad that had happened.
Actually, there was no power here. The institute was on generator, and today the generator was failing again and again.
Oh, okay, okay.
So that's why.
Yeah. But I'd like to thank you, Sushan. Thanks a lot. Your sessions were really very nice. And for your
Thank you very
project,
much.
I would be the first one to register. It sounds so interesting. I never knew there was so much to neutron stars. Actually, honestly, when you said 4 lectures on neutron stars, I was wondering what will 4 lectures on neutron stars? It's so much. But there's thanks. I think your sessions were really very nice. And it was really enlightening to know that there's so much about neutron stars. And like I said, the project is also sounds so interesting that I would be the first to register for it. And so the others can get in touch. And actually, we have a licensed Zoom. So
Yeah.
if that has to be used to do sessions, I can share that with you, and you can use that for.
Yeah, that would be lovely if if there are a number of people who wish to do the project and
Yeah. So we can give
we need
people some
to
time to
discuss.
register.
Then
Yeah, sorry. So we can give some people some time to register. And when we
yeah,
have to
sure,
have
sure.
the Zoom sessions, then I can share the password with you, or I can host it or whatever, so that we can have it on
Okay.
this licensed one.
Yeah.
In
So
the
let us see
licensed
how many
one,
people are
there are some,
interested in this,
yeah.
and then
But like you see, the
we
problem
can
is
take
what
it
has
forward.
happened for many students. You see, participants look less to you. But the problem, like,
Mm,
is even in our university, our students are
mm,
giving exams now. So most
mm.
universities now are conducting exams. So lots of the participants have even personally written to me that we can't attend the sessions because we have exams going on just now. Like I said, University of Hyderabad, even our university, they all conducted exams in this period. So I think we'll need to give them a little bit of time to watch the video at their convenience, and then we'll this thing, right? So we'll give them say a week or 10 days to tell
Yeah,
us who's
and
joining.
once we break them into groups, those who want to do with you, we can make a separate Telegram group as well,
Yeah.
so that there's not much of crosstalk and other things. So specifically, they can interact with the mentor.
Yeah. So I think you're
Then,
mute. So Sushan, let me. I think Sushan, you're frozen again, or there's another. Yeah. Okay. Yeah. Okay then. So thanks a lot, Sushan. I think again there was a problem with the net. It again froze. So you need to unmute. Uh, uh,
Yeah.
yeah. Sorry. You were muted.
Yeah. Yeah, thanks a lot. I'm sorry, this session was really disruptive.
No problem. No problem. We'll manage. Let's hope the recording, or maybe you can make a 5 minute video on the project again, and we can put that up. Because
Okay, I'll do
that
that.
project part, actually, honestly speaking, really it did get quite disturbed, right?
Yeah, I know. It got. What I will do is this week I could not do because of various. I was also not well for a few days. So what I'll do is I will prepare a short write up, which I said I'll do last time. I'll prepare a short write up and maybe a 5 minute video and send it to you, which you can
Yeah.
post.
Fine.
Then that
Yeah.
will be easier. Yeah.
That will be good, because I think otherwise the main thing won't get conveyed, and that would be at a loss, right?
Yeah. Yeah.
So
Exactly.
Yeah. So thanks a lot. And I won't talk more because I think today the net is really bad. So it's going to get stuck again. So
Okay.
thanks a lot and see you. We'll keep in
Most
touch.
welcome.
Yeah.
Most welcome.
Bye. Yeah. Bye.
Bye.